Okay, here is the example problems video. If you haven't already watched the introductory video, you might want to do that. If you feel like you're ready to rock and roll, then let's dive into these example problems. These are exactly like the ones that you'll be working for your homework. So first we're going to be working completing the square problems, and we're presented with this problem: v squared plus 8v minus 17 equals 3. So the very first step is to actually rewrite this, because we're going to need to work with it. So we have v squared plus 8v minus 17 equals 3. The very first step with these problems is to move any constant term over to the right side of the equal sign. Okay, you're trying to isolate the variables only. And so we'll do plus 17 on both sides. On the left side, the negative 17 and positive 17 cancel out. And on the right side, 3 plus 17 is 20. So you have v squared plus 8v equals 20. Okay? And now you're actually ready to do the completing the square part. And so the completing the square part is you take half the middle coefficient, which would be half of 8, and then you square it. Okay? So over in side work, I'll just do this to remind you of the graphical representation of what you're doing. You started with a square whose side lengths are always x. So this was x, and this is x. And so if you multiply x times x, you get x squared. I guess I should use v, since this example has the v component. So the side lengths are v and v. V times v is v squared, and there's the v squared. Okay? And so the next part of it is 8v. And so what we need is, let me try to fix the lighting here. Let's see what I can do without making a huge mess. Okay, we're going to have a shadow, but it might be better. It won't keep going brown. It keeps turning brown. Okay, so then we've got this other little rectangle piece, and that's always kind of sitting out here. And right now, before we erase, this has a width of 8, okay, and a length of v. And so if you were to multiply 8 times v, you'd have 8v. And so that's v squared plus 8v. And what you're going to do now is take half the middle coefficient. So that's the middle coefficient, that 8. And you're going to take half of it. And so visually what that looks like is you're going to divide that rectangle in half. You're going to clip off the right side, that little sliver, and go paste it down here. So you're going to have two little rectangular slivers, and each one of them is going to have a width of 4 and a length of v. So you always have to erase that first one and redraw like this. Okay, so now you got these two little pieces. Their widths are 4 each, and the lengths are v. Okay, so if you want to know the missing piece, that missing square down in the bottom right, you have to multiply 4 times 4. Okay, so that's 4 squared, or 4 times 4, which equals 4 squared, which we know equals 16, but we'll wait on that because we're going to need that in a minute. Okay, so once you find half the middle coefficient and you square it, you add this to both sides. So you're going to add 4 squared to both sides. Now, on the left side, what you have is a perfect square trinomial. Perfect square because the initial term is a perfect square and the final term is a perfect square. And so all perfect square trinomials can be factored into perfect square binomials like this. V plus 4 squared. First term, last term squared. Plus in the middle. Okay? Equals. And now we've got to figure out what 4 squared is. Well, 4 squared equals 16. 4 times 4 is 16. 20 plus 16 is 36. So we're going to put a 36 right here. And now what we're going to do is square root both sides of this equation in order to get v plus 4 out from underneath that squared symbol. And so now we're going to take the square root of v plus 4 squared, and so we end up with v plus 4. And this process happens like this every single time. And then you have the square root of 36 is just 6, so it's plus or minus. Remember, it's plus or minus 6. And now you can subtract 4 from both sides. And you have v equals negative 4 plus or minus 6. And so remember, the fundamental theorem of algebra states that you always have two solutions. And so v1 is going to be equal to negative 4 plus 6, and v2 is going to be equal to negative 4 minus 6. So negative 4 plus 6 is positive 2. Negative 4 minus 6 is negative 10. And so your two solutions are 2 and negative 10, which you could write like this. Negative 10, comma, 2. And what that means is that this graph crosses the x-axis at negative 10 and positive 2. Okay, so let's go look for that. 2 and negative 10. Usually we would list them with the negative number first, like this, but that's the answer. Moving on. Here's number 2. All right, x squared plus 8x plus 12 equals 6. So let's get into it by rewriting this. Give me just a second. Need to get the pencil lead correct. All right, here we go. So now we've got x squared plus 8x plus 12 equals 6. Now the first thing you always want to do is make sure there's no leading coefficient here. If there was one, you'd have to divide every term by it before you begin this process. Then you're going to subtract 12 from both sides, because we always start by subtracting the constant from both sides. And you have x squared plus 8x equals 6 minus 12, which is negative 6. Okay, now the fun begins. We take half the middle coefficient and square it. So we're not going to draw the square in the rectangle this time. We're just going to say 8 divided by 2 squared, right? Well, 8 divided by 2 is 4. And so we're going to say this is equal to 4 squared. Now we know 4 squared is 16, but we're going to write plus 4 squared on both sides. Okay. And so now I've got x squared, perfect square, plus 8x plus 4 squared, perfect square trinomial. Now we can factor into a perfect square binomial like this. X plus 4 squared equals -6 plus 16. Maybe over in side work, we do -6 plus 16. And you see that that gives you positive 10. All right, so this equals 10. Now we take the square root of both sides in order to free that x plus 4 from underneath the squared symbol. And remember, we get square root of x plus 4 squared is x plus 4 equals plus or minus the square root of 10. Now 10 is there, if you take the prime factors as 2 and 5, there's no way to reduce that, so we'll just leave it as square root of 10. Subtract 4 from both sides to isolate the x variable, and you have x equals -4 plus or minus the square root of 10. And so you got those two solutions, remember? You got x equals -4 plus square root 10. And that's x1. And then x2 is equal to -4 minus the square root of 10. And so your two solutions would be -4 minus square root 10, comma, -4 plus square root 10. There they are. Okay, so we'll go find that answer here. And let's see. Okay. Number 3. Number 3, we have a leading coefficient, so we're going to have to divide everything by 5 before we begin. So this is going to be a little more challenging. We have 5m squared plus 18m minus 19 equals 8. And now what we want to do is divide everything by 5. So every single term gets divided by 5. We have to do that before we begin because there can't be any number in front of the leading coefficient. So we'll divide everything by 5. And the easiest way to handle this is to just leave it. Don't try to come up with some decimal or anything like that. So those will cancel and everything else we'll just leave as fractions. So we have m squared plus 18 over 5 m minus 19 over 5 equals 8 over 5. Now this looks hard, but it really isn't. So just follow the process. Now we have a leading coefficient of 1, so we can just add that constant term 19 over 5 to both sides. Add 19 over 5 to both sides. Add it on the left. Add it on the right. Okay, they cancel out on the left. And so now you've got m squared plus 18 over 5m equals 8 plus 19 over 5. See, we can write it this way because they have common denominators, 5 and 5. So we can write 8 plus 19 over 5, just like that. Well, 8 plus 19 is 27, so we'll get to that in a second. But now we have to take half the middle coefficient. So in this case, the middle coefficient is 18 over 5. See, over in side work, the easiest way to do this is to multiply it by 1/2. So you take 18 over 5 and you multiply it by 1/2. And just multiply across the top and across the bottom, and you get 18 over 10. Okay. So my recommendation here is to simplify this fraction down to 9 over 5. You just divide the top and the bottom by 2, and you get 9/5. So this is the number that you square. So we're going to square this number. Remember, you take half the middle coefficient, and then you square that half the middle coefficient. And so we're actually going to write this just like this for now. I'm going to go over here and put plus 9/5. And we're going to put that in parentheses and square it. And then over here we'll put plus 9/5. And we'll put that in parentheses and we'll square it. Now we're going to figure out what that is, but first we're going to write our perfect square binomial. See, we have a perfect square trinomial, even though it looks kind of messy. We have a perfect square with m squared, and then over here we have a perfect square of 9/5 squared. And so my perfect square binomial for this problem, give me a second here to get the lead fixed on this pencil. My perfect square binomial would be open parentheses m plus 9/5 close parentheses squared equals. Okay, so you don't ever have to figure this out on the left side, but over here we're going to have to, obviously we're going to have to work with this. And so we can do 8 plus 19, that's 27, and we can write 27 over 5. And now in order to add this, we have to actually square it. So we're going to take 9 over 5 and we're going to square it. So remember the rule. This is side work. Okay. Remember the rule for squaring a fraction. When you square a fraction, you actually distribute that squared term to the numerator and denominator. And so it's 9 squared over 5 squared. Well, 9 times 9, 9 squared is 81. And 5 squared is 5 times 5, which is 25. And so we actually have 81 25ths. And that's what 9/5 squared is. And so we're going to go down here and write 81 over 25. All right. Now, we need to get common denominators in order to proceed. And so we have to multiply 27/5 times 5 over 5. So we have 27/5. And we're going to multiply that by 5 over 5. Okay? So that equals. Now, the way I do this is I say to do 27 times 5, I say, well, 20 times 5 is 100. And 7 times 5 is 35. So 27 times 5 must be 135. And so that's 135 over 25. Okay? And so let's write our step down. We got 135 over 25 is just 27/5 scaled up by 5. And so over here we'll still write m plus 9/5 squared. But now we have common denominator. So we can write 135 plus 81 over 25. Just like that. Okay? And so now we need to add 135 and 81 together. So again, we got a little bit of scratch work space left over. Let's do that. 135 plus 81. Okay, so we'll just add this. 5 plus 1 is 6. 3 plus 8 is 11. Carry the 1. 1 plus 1 is 2. And so I got 216. How about you? So we're going to rewrite the left side yet again. M plus 9 over 5. And this is squared. We're just waiting to take the square root of that. Equals, and it's 216 over 25. Okay, we are now prepared to take the square root of both sides. And so we'll take the square root of the left side and the square root of the right side. Excellent. And so when we square root m plus 9/5 squared, we just get m plus 9/5. Okay, and over on the right side, the square root of 216 over 25 is equal to the square root of 216 over the square root of 25. We mustn't forget the plus or minus, since there will be two solutions, the fundamental theorem of algebra. And now all you have to do is subtract 9/5 from both sides. Okay, and we got m by itself, just like that. Kind of suddenly that it happened, didn't it? And so over here we have, if you can follow my thinking here, it'll make sense. What's the square root of 25? It's 5. Okay, so we're going to subtract 9/5 from both sides. When I do that, I can write this: negative 9 plus or minus the square root of 216 all over 5. Since the square root of 25 is 5 and 5 is 5, I can combine these two because they actually have common denominators. The square root of 25 is 5. And so I can write it like this. I put the negative 9 up front and I leave the square root over here. And now we've got to think about simplifying this square root, because 216 can be simplified. Okay? And so what we're going to do is prime factor 216. So over here, we'll create some more side workspace. And we're going to write 216. Now, the easiest way to prime factor 216 is to just start by dividing by 2, because it's an even number. We know it can be divided by 2, and that would be 108. So 2 times 108. But 108 is still even, so we can divide by 2 again, and that would be 54. We can divide by 2 again, and that would be, what would that be? Let's see, 25. So it would be 2, and then 2 goes into 5 twice, so it would be 27. Okay, it would be 2. It would be 2 times 27. Okay, and 27 can be divided. That's 3 times 9, so that can be 3 times 9, and then that can be broken down into 3 times 3. Okay, so prime factoring 216 actually reduced everything down to primes. And so we're going to rewrite our solution. The square root of 216, follow this logic, folks. The square root of 216 is equal to the square root of all these primes multiplied together. So that's 2 times 2 times 2 times 3 times 3 times 3. Okay? Well, any pair of 2's can come out because we can rewrite this as equals the square root of 2 squared times 2 times 3 squared times 3. And you take the square root of something squared, you just get that thing. And so basically, essentially, you pull these squared terms out almost like you're factoring them out. It's not exactly the same, but it's kind of the same. So you get 2 times 3 on the outside. And so the result is 2 times 3 square root 2 times 3. And that is equal to 6 square root 6. And so 216, you think about it, the square root of 216 can be simplified down to be 6 square root 6. And so we're just going to rewrite it as 6 square root 6, since that's the simplified root. So m equals -9 plus or minus 6 square root 6 all over 5. Okay, so we have two solutions here. M1 is equal to -9 plus 6 square root 6 over 5. And M2 is equal to -9 minus 6 square root 6 over 5. Okay, so those are your two solutions. And let's go find those. Did you think that you were going to find one of these? They look like they're impossible, but look at that. It's right here, D. Very cool. This is what math is. This is when math gets really fun, especially over in here. I really enjoy this. Okay, so we're on to the next problem. Let's look at number 4 here. And at this point, you're either having a lot of fun with these or you're miserable. And I can sympathize with both sides because I definitely used to be the latter student, being miserable. But once I practiced them a lot, I started to like doing them because it was easier to do. Okay, so we're going to start by rewriting it. 6a squared minus a minus 19 equals -7. Okay, 6a squared minus a minus 19 equals -7. Here it's going to be very important for us to remember that there is a 1 in front of that a. Okay, because we have a leading coefficient that is not 1. And so the very first step is to divide every term by 6. Okay, so every term gets divided by 6 so that we can get the leading coefficient to be 1. Cancel, cancel. So we have a squared minus 1 over 6a minus 19 over 6 equals -7 over 6. Okay, we're on our way. And so what do we do next? We've got to remember, we just got to move this over here. Get that -19 moved over so it's plus 19 over 6 on both sides. Okay, cancel. And now we have a squared minus 1 over 6a. Leave a big space. And now you've got negative 7 plus 19 over 6. Okay? And so now we have to take half the middle coefficient and square it. So over here in what we'll now call side work, leave a space right here. Okay? You're going to write something there in a second. We're going to take negative 1/6. Ooh, it's very important to remember that sign. And we're going to multiply it by 1/2. Okay? And negative 1/6 times 1/2, we'll just multiply across the top. You get negative 1 times 1 is negative 1. Over 6 times 2 is 12. And remember, we're going to square that and add it to both sides of the equation. So we're going to put plus negative 1 over 12 squared and plus negative 1 over 12 squared on the left and on the right. You now have a perfect square trinomial on the left that you can factor into a perfect square binomial as a, and this is why we wanted to make sure we kept that sign, a minus 1 over 12 squared equals. And now we get to have fun over here. So back to side work, we're actually going to square this thing out. We have negative 1 over 12, and we're going to square it. Now, when we square it, we distribute the squared symbol to the numerator and denominator, so we have negative 1 squared. Here, the negative sign is going to go away because anything negative squared is positive, and then 12 squared. So negative 1 squared is 1. 1 times 1 is 1, or negative 1 times negative 1 is 1. Over 12 squared. 12 squared is 144. Okay? Which brings this into focus. Now we know we're going to end up needing to make that 6 turn into 144. So first let's add negative 7 to 19, which would make it 12 over 6. Aha! So negative 7 plus 19 over 6. There's going to be a little trick in here. Negative 7 plus 19 is 12. So that equals 12 over 6. Well, 12 over 6 is just 2. 12 divided by 6 is 2. And so we're going to write 2 over 1 to leave it as a fraction. And then we're going to multiply by 144 over 144 so that we give that denominator 144. Well, 2 times 144 is 288. Just double it in your head. Over 144. And there you go. Bob's your uncle. You ever heard that phrase before? Bob's your uncle. And now we just need to add 288 plus 1. So that's this plus this over 144. So I'm doing all of this stuff over here in side work. Well, that's equal to 289 over 144. And so that is actually what negative 7 plus 19 over 6 plus negative 1 over 12 squared equals. It's 289 over 144. So we'll write 289 over 144. Well, now what do? Okay, even though the numbers look big, we still take the square root of both sides. And there will be some magic happening here with simplification. So we're not going to end up with big numbers. Okay, so when you take the square root of a minus 1/12 squared, you get a minus 1/12. And that equals the square root of 289 over the square root of 144. And we mustn't forget to put the plus or minus symbol in front of all that, because it could be plus and it could be minus. And so we know that the square root of 144 is 12, but what about 289? So let's go over to side work and let's think about 289. Just kind of sectioning off the side work here. So we're going to take 289 and we're going to start to break it down. Now let's see what it's divisible by. 2 plus 8 is 10. 10 plus 9 is 19. 19 is not divisible by 3. So that's not a factor. It's an odd number, so it's not divisible by 2 either. So we go up to 4. Can you think of anything multiplied by 4 that ends in a 9? I can't. How about 5? Nope, it's not a 0 or a 5. How about 6? It could be divisible by 6. Let's try. If you do 6 into 28, you get 4. That's 24. There's 4 remainder, and then it's 49. That's not an even divisor. How about 7? 7 goes into 28 4 times, and then you have a remainder of 9. That doesn't work. How about 8? 8 goes into 28 3 times. That's 24. You have 4 as a remainder, and then 9, 49. Nope, 8 doesn't go into 4. How about 9? 9 goes into 28 3 times with 1 as a remainder, and then you have 19, but 9 doesn't go into 19. You know what I'm starting to think? I'm starting to wonder if it might be like 11 or something. But if it's going to be 11, we are going to need to check our calculator, because we're starting to get up above the pay grade here. So let's do 289. Let's try dividing by 11. Nope. How about 289 divided by 13? Nope. What could it be here? 289 divided by, can't be 17. It is 17. Okay. So 289, this was a tough one. 289 divided by 17 equals 17. And so it's actually 289 is a perfect square of 17 and 17. I never would have figured that out without a calculator. 17 and 17. Those are hard. Okay. Never in a million years would I have figured it out. Okay. So breaking that down, we see that we get a perfect root. All right, so the square root of 289 is 17. The square root of 144 is 12. And so we say a minus 1 over 12 equals plus or minus 17 over 12. Okay, now we add 1/12 to both sides. Okay, and it cancels out over here on the left side, and now we have a equals, and you have common denominators here. You have a equals 1 plus or minus, don't forget that, 17 all over 12. So we have a1 is equal to 1 plus 17 over 12. A2 equals 1 minus 17 over 12. All right, so we can simplify these. We're not done yet. So these both get simplified further. 1 plus 17 is 18. So now we have 18 over 12, and we can simplify that fraction. 1 minus 17 is negative 16 over 12, and we can simplify that fraction. So 18 and 12 have a greatest common factor of 6. So if we divide the top and the bottom by 6, we get 3 over 2. Okay? And over here, 16 and 12 have a greatest common factor of 4. If we divide negative 16 by 4, we get negative 4. If we divide 12 by 4, we get 3. And so here are our two solutions, negative 4 thirds, comma, 3 over 2. Let's go find that answer. 3 over 2 and negative 4 thirds. How about that? It's pretty good. We did have to touch on the calculator there to get that 17. I gave up. I didn't want to just keep testing numbers. Who knows their tables up to 17, for heaven's sakes? Okay, there's probably some people that do. All right, we're on number 5. And here we're getting into the complex number situations. So let's follow the yellow brick road, as it were, and see where it takes us. Okay. Going to do that, I've got to get the pencil lead to be, I don't know if you can see this. I'm trying to get the pencil lead to be at an angle so I can write. All right, so now I'm going to start with k squared. I don't know if that's just a lefty thing or if other people do that, right-handers. K squared plus 14k plus 59 equals 4. So a quick check. The leading coefficient is 1, so I can just proceed to subtract 59 from both sides. Okay. So now I've got k squared plus 14k equals 4 minus 59 is negative 55. Okay, and so now remember we take half the middle coefficient and we square it. So over here in side work we'll take 14 and we'll divide by 2 and we get 7. Okay, and then we square 7. 7 squared. So we can just write plus 7 squared plus 7 squared. We have a perfect square trinomial on the left. K plus 7 squared can be factored into the perfect square binomial. K plus 7, the whole thing squared, equals. And now it's negative 55 plus 49. And so 55 minus 49 is going to be negative 6, because you're going to basically subtract 49 from 55, and 55 minus 49 is 6. And so you just put a negative sign in front of it. And so this whole thing, k plus 7 squared, equals 6, negative 6. Okay, now because it equals a negative number, we're going to end up with imaginary number solutions. Okay, so we're going to take the square root of both sides. I'm going to walk you through the whole thing, so don't worry. Take the square root of both sides, and now you have k plus 7 equals the square root of negative 6. Okay, so how do you deal with the square root of a negative? Well, here's how you deal with it. go over here and remember that the square root of -6 can be written that's equal to the square root of -1 times the square root of 6. And remember that the square root of -1 equals the imaginary number I. Okay, so we can just substitute in here, like therefore, that was definitely the wrong symbol, a semicolon when we're doing imaginary numbers. What are you thinking? Therefore, we have I square root 6. Okay, so we go back here and we just write k plus 7 equals, and I'm going to write the square root 6 first, square root 6i. It's multiplied. It's square root 6 multiplied by I. All right, so now we're going to just subtract 7 from both sides. Remember, this is plus or minus. Should always remember that. And so cancel out the 7s, and now we have k equals. All right, what does k equal? K equals -7. You always write the real number first, plus or minus the square root of 6i. Okay, so your two solutions, they're both imaginary, but they're both, we actually do have two solutions. Now, I'll show you what that means here in a second. You have -7 plus the square root of 6i, and you have -7 minus the square root of 6i. Now, here's the deal. This is called the rectangular form of your complex numbers. So you have the real number component and the imaginary number component. And those can be plotted on the complex plane like this. You've got your real axis. That's this horizontal axis. That's the reals. And you've got the imaginary axis, which is the vertical axis. Imaginary. Now, you can think of it like x and y. All right, so if you wanted to plot these two coordinates, you would just need to plot out 1, 2, 3, 4, 5, 6, 7. And so -7 is just -7. It's just the real numbers, okay? So it's just here at -7. You can think of this, by the way, like x and y coordinates. So this is your x coordinates and this is your y coordinates. You can kind of think of it like that. And so what you're really doing, if you want to think about it, K1 is going to be plotted at -7 comma square root 6. And K2 is going to be plotted at -7 comma negative square root 6. All right. So it might be useful to find out what the square root of 6 is, since we need to know that. Hang on a second. All right, we want to find out what the square root of 6 is. So you take 6 and then hit that second root, 2.45. Close enough, 2.4. And so this is approximately equal to -7 comma 2.4 and -7 comma -2.4. And now we can label these correctly. This is like real comma imaginary. All right. So we'll just say this is -1. And by the way, so when you have these on the imaginary plane, it's just the same thing as the real number plane, but you put an I after it. So this is like -1i, -2i, -3i. Okay. And it goes up the same way. 1i, 2i, 3i, 1i, 2i, 3i. It's pretty easy. And so to plot these points, it's -7, 2.4. That's -7 on the real, 2.4 on the not fake, imaginary. -7, 2.4 would be about right there. Okay? And then you have -7, -2.4. And so that would be about right here. And so these are actually solutions. Okay? So the complex coordinates right here are -7 plus square root 6i. And down here it's -7 minus square root 6i. And just as a little preview, the thing that's really important is to determine the magnitude of this line. And you do that by forming a little triangle like this. And it's a right triangle. Okay. You know the base is -7, right? And you know the height is the square root of 6. So the height's the square root of 6 and the base is 7. And so what you want to find is the hypotenuse. And so you just use the Pythagorean theorem. Okay. I'll show that here. And this is called, what I'm doing right now, finding the hypotenuse of this. This is called an Argand diagram that we're drawing here. So I'm going to put some verbiage down. Argand diagram, where we're plotting the real and imaginary. The Argand diagram. And what we're about to find is we're about to find the radius of a circle. So here comes the compass out of nowhere. The point of the compass goes at the center of the coordinate plane, and then the pencil goes on that point. And now I'm going to rotate a circle through this coordinate plane here. Okay? So I'm pretty sure that should have landed. This second point should be on that circle. It was close. It's got to be on the circle, though. Okay, so there it is. Now we're going to figure this out. So we're going to find... I mean, we're done with the problem, but I'm just showing you something that's going to come up on the next assignment. We're going to find that orange line. By the way, the answer was right here, B. But we're going to just stick with it, okay? It's important. So just look at that picture for a minute and think, did you think that imaginary numbers were going to take you to a place where you were using a compass to make a circle? And now it looks very familiar, doesn't it? It looks like we're just going to we're going to use Pythagorean theorem. That's all we're going to do. Okay. So we take -6. Let me show you exactly what I mean. This is important. If you're actually paying attention right now, you're about to learn something. So we're going to just draw. I'm just going to go down here and draw this triangle. Okay. All right. So this triangle has a height of square root 6 and a base of 7. It's a right triangle. And so we use the Pythagorean theorem. All right. So this can be A. The 7 can be A. The square root 6 can be B. And then we have the hypotenuse, which is C. Well, A squared plus B squared equals C squared. There's your Pythagorean theorem. So 7 squared plus square root 6 squared equals C squared. Well, 7 squared is 49. The square root of 6 squared is just 6, so it's plus 6 equals C squared. Well, 49 plus 6 is 55. So you have 55 equals C squared. And then you take the square root of both sides. And remember, for geometric purposes, we only consider the positive roots. The square root of 55 is equal to C. Okay? So 5 55 only has two factors, and that's 5 and 11. And so there's no way to simplify it. So you just say that square root 55 is equal to c. And what this is called, the square root of 55, is called the modulus. And that's modulus, the modulus of negative 7 plus square root 6i equals the square root of 55. Okay, and what that is, what the modulus is it is the radius of this circle. Okay, so you can go in here and put it down, square root of 55. Okay, what is the square root of 55? Just so we can get a kind of understanding of it. Let's go see. 55 square root 7.4. Okay, so this is like 7.4 units long. Pretty cool, huh? And so that's pretty. I'm going to stop. Just stop with that problem right there. You just found the modulus of a complex coordinate. Okay, you just found the modulus of a complex number. Negative 7 plus square root 6i has a modulus or a radius of square root 55, or something like 7.4. Pretty interesting. And definitely, if you were paying attention just now, you learned something that you did not know before. Now, it turns out that this rotation angle is extremely important, and that's going to come into play later. But just to give you a preview, what you would do is, and we'll later when you get older and you get ahead in your math classes, you're actually going to use trigonometry to find this. But you really want to know what this angle is. This is important. So that whatever this angle is very important, and we'll get that angle right now. Okay, so it looks like it was almost exactly at 145, maybe 146. Okay, we'll use trigonometry when you get older to find out exactly what that was, and be able to determine what this angle is right here, this angle of rotation counterclockwise this way. Okay, so we want to know what this entire huge angle is right here, and that is called the argument of the complex number. So if you wanted to find it, what you would do is, I'll show you what you would do. Let me show my display and then give the calculator right here. What you would do is, let's make sure that we are in degree mode. If you wanted to know how many degrees that was, well, yeah. All right. First, we'll do degrees. And so what you would do is you would do something called the arctangent, or the inverse tangent of square root 6 over 7. Square root 6 over 7 would be here. Right? So there's the arctangent. And let me go back to the screen so you can see what that 0.3366 actually means. No, it's supposed to be showing it to us in degrees. Hang on a second. Because what we were just looking at is in radians. So let me do that again so we get the degrees. There, 19.28 degrees. Let me go back to the math problem so I can show you just what I'm talking about here. Okay, what that means is that what we just found was actually this angle right here was 19, whatever it said, 19.28, so 0.286, so 19.29 degrees. And if you wanted to know what this angle is, you would subtract that from 180. So 180 minus 19.29. Let me show you kind of how that works. So hang on a second here. You would just take 180 minus that. Okay, boom, 160.71. So basically that angle was rotated 160.71 degrees counterclockwise from the origin. So going back to radian mode, I'll show you something cool. Going back to radian mode and then hitting second quit. Let's compute this again. Okay. Now, in radians, it's 0.3366. If you're in my geometry class, you already know what this means. And so what we can do is we can take pi minus that, all right? So let me go back to my picture for a second, just so we can look at what we're talking about. In the future, when you get into geometry and algebra 2 and beyond, you will learn about something called the unit circle, and that unit circle is labeled with different points. For example, 90 degrees counterclockwise rotation from the origin is labeled pi over 2. 180 degrees counterclockwise from the origin is pi. Okay, just for these purposes, that's all we need to know. Over here, it's 3 pi over 2. And then over here, it's 4 pi over 2, or just 2 pi. Okay, so it just goes 1 pi over 2, 2 pi over 2, which reduces down to pi, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, blah, 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 round and round. So looking at this, what you could do if you were using radians, which would be the measure of the arc around the circle, you would just take pi and then subtract the radian measure that you found when you took the arc tangent. Okay, because basically you found with this arctan of 0.3366. Let me show this to you again. You need to see it. This arctangent of 0.3366, let me show you exactly what that means. 0.3366. What does it mean? Let's go back here. Let me transition out of this. Okay. What that means is that this portion of the arc is represented by 0.3366. And so if you subtract that from pi, which is this entire 180 degree rotation, you will have this arc measure. Okay. I wish I had another way to do this, but let me just show it to you. You would have this arc measure in blue. Okay. So if you want to know that arc measure, you just take pi, okay, which we can approximate as 3.14159.265, and what you would subtract out of it is that radian measure that you got, 0.3366, which it went out further. It was 0.336609879, 0.336609879, 0.9879. Well, we'll just round to the nearest, so it would be 8 right there. Okay, and so we want to subtract these two things. All right, well, this is just pi, and this is the arctangent of square root of 6 over 7. So, so what we want to do is we're actually, let me get my display capture back on. What we want to do is we want to take pi. You can get that pi symbol right there, pi, minus that, all right? And this is going to give us that blue arc. Ready? Boom. 2.8049. Well, let's go back to the work surface. Okay. 2.8049. 2.8049. And that corresponded to 160 degrees. Okay. 2.8049. Now, what this is, this 2.8049, this is the arc measure, okay, arc measure from the starting point counterclockwise all the way to here, 2.8049 radians. Now, the way to do it, kind of the appropriate way to do it, would be to take what you would want to do is you would want to take your well, we'll just leave it there for now. So so the modulus of this thing is -7 plus square root 6i. The modulus of it is the square root of 55, and the argument is equal to, I like to write it in exact terms, and that exact term was pi minus the arc tangent of square root 6 over -7. Well, we'll just put 7 since we're subtracting it already. Okay, and so the kind of the approximated argument was 2.8 radians, or if you remember, it was 160.713 or 160.71 degrees. Okay, see that? So you've got, for imaginary, you've got modulus and argument. So in other words, the hypotenuse and the angle of rotation. Okay, so this was 160.71 degrees. So guys, if you're watching this, I'm not here thinking that you're following 100% of what I'm saying, and I'm not even sure I'm explaining it very well. However, what I will say is, if you're kind of tracking a little bit with this, that you're really getting a head start on major math later in life. Okay, so let's move on here to number 6. All right, so we're at number 6, and this is the last problem from the completing the square problem set. And here we go. So first I've got to make some scribbles. And we've got a squared plus 18a plus 75 equals -9. Right? Leading coefficient is already 1, so we can just proceed to subtract 75 from both sides. Okay, minus 75 from both sides. And we get a squared plus 18a equals, and then -9 minus 75. It's like adding 9 and 75, guys. So that's 84 with a negative sign in front of it. -84. And so now we're going to take half the middle coefficient and square it. You take 18 and you divide by 2, and then you square the result. Well, 18 divided by 2 is 9. 9 squared, that's going to be 81, but we'll put plus 9 squared. And I guess over here we can just put plus 81 since we know what's up. We know we're going to eventually do that. Now we have a perfect square trinomial that we can factor into a perfect square binomial. A plus 9 squared equals, and then -84 plus 81 is -3. Okay. Well, now we take the square root of both sides. Take the square root of the left, take the square root of the right, and you get a plus 9 on the left equals the square root of negative 3. Well, remember, the square root of negative 3 can be written as the square root of negative 1 times the square root of positive 3. And the square root of negative 1 is I. Square root of negative 1 equals I. And so, therefore, that's what these 3 dots mean. We have square root 3 I. Okay? So there's your imaginary number. You have a plus 9 equals square root 3 times I. And you'll get to where you just do it in your head. And now you subtract 9 from both sides. Remember, this is plus or minus. And so these cancel out, and we have a equals negative 9 plus or minus square root 3i. Well, that gives us 2 solutions, doesn't it? We have the first solution equals negative 9 plus square root 3i. And the second solution is negative 9 minus square root 3i. Okay, don't forget your complex coordinates. So this is the real part, and this is the imaginary part. And you can write them just like coordinates. Okay, so A1 as complex coordinates would be negative 9 comma square root 3. A2 as complex coordinates would be negative 9 comma negative square root 3. Okay? So on a coordinate plane, the complex coordinate plane, where the horizontal is the real and the, well, I drew that wrong, and the vertical is the imaginary, or non-real, or lateral numbers, whatever. Make this more like this. Since the real component is negative 9, let's make it try to look good. So this is negative 1, negative 2, negative 3, negative 4, 5, 6, 7, 8, 9. That's negative 9 right there. And then square root 3. You know how we could do this in a clever way? We could say, well, I don't want to be clever. I just want to find out what the square root of 3 is, if it's okay with everybody. Let's just take 3 and then take the square root. 1.732. Should have had that memorized. And so here is 1i. Here is 2i. Here is 3i. And it goes in the negative. Here is negative 1i, negative 2i, negative 3i. So you can plot these coordinates. Negative 9 comma square root 3. If the square root of 3 is 1.73, it's going to be almost to 2. So you just go up here, put a dot right about here. And then it's just the opposite of that, right? It's down here beneath the 9, but before the negative 3i right there. So there's your complex coordinates. Remember how to find the modulus. If you want to find the modulus, okay, you have to create a triangle. And this base is negative 9, and the height is the square root of 3. So you can almost do it in your head. You've got a squared, which is negative 9 squared, plus b squared, which is square root 3, so square root 3 squared, equals c squared, which we don't know. Okay, so negative 9 squared, that's positive 81, plus square root 3 squared, well, that's just 3, equals c squared. And so whatever the square root of 84 is c. because you're going to take the square root of both sides to get c by itself. So this is the square root of 84. But we can probably break down 84 into 2 times 42, which is 2 times 21, and that's just 3 times 7. So we could rewrite the square root of 84 as 2 square root 21. Okay? So the modulus, all right, of the modulus of this first solution here, negative 9 plus square root 3i, is 2 square root 21. That is the hypotenuse length. Okay, this is really important stuff. It's not just making this stuff up. This is some heavy duty math. All right, so answer is right here. At this point, that's almost the easiest part, is getting the answer. And that brings us to the next example problem set, which I will reserve for a separate video. Okay, guys, thanks so much for watching. You have learned an enormous amount, especially if you're paying attention. You have learned an extraordinary amount of information here in this tutorial set, more than even I anticipated delivering. Certainly, if you have mastered this, you have mastered all of Algebra 1 and pretty much all of Algebra 2 and all of geometry. And if you're struggling to get there, understand that when you shoot for the stars, if you fall short, you'll land on the moon. Okay, so you aim for the stars, and you'll land on the moon. All right, so that's why we're punching up here. We're shooting very high, trying to get you to do things that are complicated. All right, because if we were just doing easy stuff and you're not challenging yourself, then you're not growing. You know, if you're not pushing yourself to make that next step and learn more, then you're not growing. And so you always want to be at the bleeding edge of what you understand. Always trying to push yourself to that next thing that you don't understand. Just do one more problem, learn one more concept. You know, it's like when you're bench pressing, just go through one more rep, you know, beyond you can barely do it, and you'll finally lock out and rack those weights, and you'll feel like, man, I accomplished more than I ever have before in my life when you bench beyond your max. So, guys, thank you so much for watching this video, and join me in the next video where I'll start working these imaginary numbers example problems. They're actually really easy. So, thanks so much for watching.